Welcome to Math with Professor V. This is video lecture for section 6.3 for business calculus on further business applications. So the first idea that we're going to go over is economic lot size. Here's the idea. Suppose a company manufactures a constant number of units of a product per year and that demand for the product is constant. So these are two necessary assumptions. You're making the exact same quantity of some product every year. The product can be manufactured in several batches of equal size throughout the year. So how do we want to go about producing it? Well, on one hand, if the company were to manufacture just one large batch every year, that would minimize setup costs but incur higher warehouse costs. On the other hand, if the company were to make a bunch of small batches, then that would increase setup costs. So where's the happy medium? How do we know how many batches and how often to make them? What size should the batches be? Well, thankfully we have calculus, and calculus can be used to find the number that should be manufactured in each batch in order to minimize total costs. Because from a company's perspective, you always want to minimize costs. That way you can maximize your profit. So here are the considerations. Q represents the number of units in each batch. K is the cost of storing 1 unit of the product for 1 year. F is the fixed setup cost to manufacture the product. G is the cost of manufacturing a single unit of the product. And capital M is the total number of units produced annually. Okay, so let's define some further quantities so we can come up with what our total cost function is. So first thing we want to think about is, what is the cost to produce each batch? Well, there's two components to that. There's the fixed cost and the variable cost. The fixed cost is represented by lowercase f, and then the variable cost we're going to compute this way. The variable cost is the cost of manufacturing a single unit times however many units are in that batch, right? So the variable cost would be given by G times Q. Good. Okay, what about the total manufacturing cost? Well, that would be whatever the cost is per batch times the number of batches that you make throughout the year. Well, we just figured out what the cost was per batch up above. That's F plus G times Q. Now I want to multiply that by the number of batches that we make in a year. So what would that be represented by? Well, M is the total number of units that you need to produce, and Q is the number of units in each batch. So if I take M and divide it by Q, that would tell me the total number of batches that we're making. So I can go ahead and simplify this a little bit. Let me take M divided by Q and distribute it through. So now my total manufacturing cost would be FM divided by Q plus, notice this Q and this Q will cancel when I distribute, so it'll just be GM. Okay, that's the manufacturing cost. Beautiful. What about the storage cost? That's another consideration. Okay, well, the total storage cost would be the cost to store each unit times the average number of units. And the cost to store 1 unit is represented by K. Look up top. K is the cost to store 1 unit of the product for a year. And then the average number of units is going to be Q, the number of units in each batch, just divided by 2, because that's going to be constant for the year. Okay? And this Q doesn't change per batch. Q is always the same per batch. So I can write this as K times Q divided by 2. So that's my storage cost. So capital T of Q, this represents total cost, total cost, meaning total manufacturing plus total storage cost. So I'm going to add together these two quantities that we found earlier. So that would be FM divided by Q plus GM plus K times Q divided by 2. There's my total cost, which includes total manufacturing cost and total storage cost. Well, what do you think we're going to be asked to do often? we're going to be asked to minimize the total cost. That's what every company wants to do. So think back, how would we find the minimum of this function? Well, we would find the critical number, so I need to take its derivative. And then once you have the derivative, remember we set it equal to 0 and find where it doesn't exist. So let's go ahead and start that process, okay? Since it's going to be something that we're going to be asked to do repeatedly. Now, t is a function of q. So I know there's so many variables here, your head's probably swimming, but only q is a variable. Everything else is going to be constant depending on the problem. So you'll be given what f is, what m is, what g, etc. Q is basically what you're solving for. Q is, remember, the number of units in each batch. So let's go ahead and figure out what the derivative would be and get our critical numbers. Before we take the derivative, I'm going to write t of q in a little bit more friendly of a format. So t of q, since we're going to take the derivative, I'll write it as fm q to the negative first plus gm plus k divided by 2 times q. All right, so now we're ready to take the derivative. T prime of q is going to be, bring this exponent down front, subtract 1, that's the new exponent, plus gm is just a constant. There's no q's on it. So the derivative is going to be 0. And then derivative of k over 2 times q is just k over 2. Think, like, what's the derivative of 3x? Just 3. So derivative of constant times q, just the constant. Okay, see, not so bad. So then t prime of q is negative fm over q squared plus k over 2. Okay, there's our derivative. Now let's get our critical numbers. So that happens when t prime is 0 and where t prime does not exist. So let's set this derivative equal to 0. That would mean negative fm over q squared plus k over 2 is 0. Let me move fm over q squared to the other side. So k over 2 equals fm over q squared. We can cross multiply. Do you remember doing that? Back when you were an innocent algebra student, probably. So kq squared equals 2fm. So q squared is 2fm over k. Technically, q would be plus or minus the square root of 2fm over k, but q being negative makes no sense. It's the number of units in each batch. So I'm just going to keep the positive radical, 2fm over k. Okay. So that's how we can find q that's going to minimize total cost. Now, the other thing to consider when getting critical numbers is where the derivative doesn't exist, which happens if q is 0, right? Then that denominator would be 0. But that's not really interesting for us. Like, think about it. You want to minimize cost? Yeah, let q be 0. Just don't make any units at all. There we go. I minimized cost for you. No, that's not helpful, right? So we got to make some of our product. We're not going to really consider q being 0. If you got hired for a job and they're like, help us find how many products to make in each batch to minimize cost, and you're like, I came up with it, just don't make anything at all, I don't think you'd keep your job very long. Okay, so what we're going to do now is look at an example, and all of the other values like f, m, k, those are going to be given to us. So we're going to just use this result here in the next exercise. We don't have to rederive it from scratch, and feel free to do the same thing as you're working through your homework exercises and whatnot, okay? So here we go. A manufacturer has a steady annual demand for 13,950 cases of sugar. It costs $9 to store 1 case for 1 year, $31 in setup costs to produce each batch, and $16 to produce each case. So part A says, find the number of cases per batch that should be produced. So that means find Q. Number of cases per batch, find Q. So let's identify what each of the quantities are that were given to us. So 13,950, that's the total demand. That's basically the total number of units that are produced annually. So M is 13,950. $9 is the storage cost, so that's 9 is K. Setup cost is $31. And then it costs $16 to produce each case. So little g is 16. Okay, so I don't need little g to find q. Just look up above. Q is square root 2 fm over k. So they gave me more info that I needed for part A. So q is going to be square root 2 times 31 times 13,950 divided by 9, which is the square root of 900 or 96,100. Okay. Does this have a nice square root? It sure does. 310. Whoever wrote this problem loved us dearly. So 310 cases. Perfect. That's how many cases per batch. Part B says, find the number of batches that should be manufactured annually. So remember, number of batches is M divided by Q. So if we need to make 13,950 cases in a year, and each batch has 310 cases, then we're going to be making 45 batches per year. Ooh. Almost 4 a month. Okay, good. Next idea, economic order quantity. So the company using a product must decide how often to order and then how many units to request each time an order is placed. So here are your considerations. Q is the number of units to order at each time. K is the cost of storing 1 unit for 1 year. F is the fixed cost to place an order. And capital M is the total units needed per order. Okay, so let's go through all of the further quantities to consider when we're looking at total cost. So first we have to think about our reorder cost. The reorder cost is going to be the number of orders that you place times the cost per order. So how many orders do you place? Well, whatever the total number of units is divided by however many units there are in an order. And then the cost per order is F, that was given. So this is FM divided by Q. What is the storage cost? So that would be the cost per unit times the average number of units. So this isn't any different than before. That would be K times Q divided by 2. And so our total cost, reorder cost plus storage cost, is FM divided by Q plus KQ divided by 2. So how is this different than the other total cost that we computed earlier? Well, it's just missing that term G times M. That was a part of our manufacturing cost, which is not relevant here, but the two formulas are very similar. So make sure you pay attention to which scenario you're in, if it's economic order quantity versus economic lot size. Lot size talks about batches. This is just about reordering. Okay, and then what was the formula for economic order quantity? Just to remind you, Q was square root 2FM divided by K. And that's going to be the same in this scenario as well, because the only thing that was missing was that constant term. Remember, GM is missing here. But if you go through the process of finding critical numbers, when you take T prime of Q, GM was just a constant, so the derivative was 0. So the rest of the process would play out exactly the same way, and we would end up with the same critical number for Q. The process would be identical. So I'm not going to redo it. We can just go ahead now, use the same formula for both scenarios, and look at an example here. So a restaurant has an annual demand for 900 bottles of California wine. It costs $1 to store 1 bottle for 1 year, and it costs $5 to place an order. Okay. Part A says, find the optimum number of bottles per order. So we're going to find Q. So up top, remember Q is square root of 2FM divided by K. Well, they gave me all the info I need. 900 is going to be capital M. And then K is just $1. That's my storage cost. And fixed cost is $5 every time you place an order. So Q is going to be square root of 2 times 5 times 900 divided by 1. So that's 10 times 900, which gives me 9,000. And square root of 9,000 is about 94.9. So here's our dilemma. Should it be 94 or should it be 95? Don't automatically say, oh, 94.9 rounds to 95. Not necessarily. Remember, I'm trying to minimize total costs. I'm trying to minimize the function T of Q, which is FM divided by Q plus KQ divided by 2. So what I'm going to do is take 94 and 95, substitute them in for Q, and see which one gives me the smaller value for T. Yes? Okay, well, I did it for you already. So T of 94 comes out to approximately 94.872. And then T of 95 comes out to approximately 94.868. So this yields the smaller total cost, 95 bottles. So you should have 95 bottles per order. But not because 94.9 rounds to 95, no, because the total cost at 95 was lower than the total cost at 94. So be careful. Last part, how many times a year should the wine be ordered? So remember, we need 900 bottles total, and there's 95 bottles per order. So M divided by Q would be 900 divided by 95, which is about 9.5 times. Okay, how would you handle that? I don't know, space it out evenly in a year. So some year you order 9 times, some year you order a different number. Okay, last very big idea is elasticity of demand. So let Q be a function of P. So Q is demand at some price P. The elasticity of demand is given by the following. E equals negative P divided by Q times dQ dP. So elasticity of demand, E, is a function of P, of price. We say that demand is inelastic if E is less than 1. Demand is elastic if E is greater than 1. And then demand has unit elasticity if E equals 1. So what exactly does this mean? Well, if demand is inelastic, that means the total revenue increases as price increases. So think about it this way. Inelastic demand basically is when a change in the price results in a very small change in the quantity demanded. That people will still need the same amount of the product. The demand doesn't change regardless of if the price goes up. So here's some examples. If you think about it like necessities, fuel. Most of the time when gas prices change, we complain about it, but it doesn't mean we actually make these significant differences in the amount of gas that we demand or that we use. Also utilities. If the electric company all of a sudden starts charging you so much more, you're not going to like go off the grid and stop using electricity most of the time. Prescription drugs. If the price of a prescription drug skyrockets, but it's something that you need to stay alive, to stay healthy, you're still going to demand the same quantity. Also, things like specialty coffee drinks. If you're hooked on that matcha latte from Starbucks and they double the price, probably you're still going to keep going because there isn't like a equivalent substitute. You're probably hooked on it for a reason. So those are examples of quantities where the demand is inelastic. Price changing doesn't affect how much you're going to consume. And so what happens is if a company decides to up the price, you're still consuming the same amount, so their revenue goes up. Okay, second case, if demand is elastic, then the total revenue decreases as price increases. So basically, elastic demand refers to products where consumer demand, how we behave, changes significantly when price changes. And so some examples are luxury items, dining at high-end restaurants, and first-class airline tickets. If the price increases significantly, these things are not necessities. You're probably going to cut back on how much you consume. There's a small fragment of the population that can afford these things regardless, but generally speaking, people will consume less luxury goods if the price increases because they're not essential. Also, designer clothing, consumer discretionary items, things like brand name cereal and candy bars. The demand can change in response to price changes. So just think situations where the price changes and you're like, nope, I'm out. That's too expensive. Then demand is elastic. And basically, from a company's perspective, their total revenue is maximized at the price where demand has unit elasticity. So if we're asked to maximize revenue, then what you want to do is figure out where elasticity equals 1. That's when revenue is maximized. All right, so let's look at some examples. A company determines the demand in hundreds for their novelty t-shirts to be D of P equals 400 minus P squared. So this is our demand function. We can also call it Q equals, right? Q is a function of P, where P is the price for one shirt. So part A, find the elasticity of demand E. So remember, E is equal to negative P divided by Q times dQ dP. So let's find dQ dP. I'm going to take the derivative. 400 is a constant. Derivative of negative P squared is negative 2P. So we have negative P over, how do I know I'm keeping the P's and not the Q's? Remember, it's a function of P. It's a function of P. Instead of Q down here, I'm going to write 400 minus P squared. And then dQ dP is negative 2P. So if I simplify, this is going to be positive 2P squared over 400 minus P squared. Okay, good. If the price is $5 per shirt, calculate the elasticity. Is the demand elastic or inelastic? So if the price is $5 per shirt, I'm going to substitute that in for P. So 2 times 5 squared divided by 400 minus 5 squared. So that's 50 over 375. So I already can tell it's less than 1. It's about 0.13. Always compare elasticity to 1. If it's less than 1, then what does that tell me? That means that demand is inelastic. So to answer the second part of the question, if we increase the price, that means there will be an increase in revenue. So that tells you you're the t-shirt company, charge more than $5 per shirt. Well, we up it to 15 then. Okay, I can make more money if I charge more. They're going to keep buying these t-shirts. So now the price is 15. Calculate the elasticity. So E is going to be 2 times 15 squared divided by 400 minus 15 squared. So that's 450 divided by 175, which is about 2.57. Ooh, that's greater than 1. So now demand is elastic, which means we went too far. So if we increase the price anymore, we're going to have a decrease in revenue. Oh no. That means we went too far. So we got to find the sweet spot. Find the price that maximizes the revenue. What is that maximum revenue? So remember, to maximize revenue, we want elasticity of demand to be 1. So no guessing, just set 2P squared over 400 minus P squared equal to 1, which means 2P squared is 400 minus P squared. So 3P squared is 400. P squared is 400 over 3. So P is square root of 400 over 3, which is about 1155. Ah, okay. So that's where we should price the t-shirts. Cool. Then they asked for the actual max revenue. And notice I don't have a revenue function, do I? So I have to come up with one on my own. It's fine. We know revenue is price times quantity. So we got this. revenue is price times quantity. So I already know what the price is. I just need to figure out what's the quantity that's going to be demanded at this price. Remember, our demand function Q of P was 400 minus P squared. That was given. So Q of 1155 is going to be 400 minus 1155 squared. Technically, 1155 is rounded. It was square root of 400 over 3. So if I take that value for P, square root of 400 over 3, and then I square it, the radical goes away. And this is just going to be 400 over 3. That's more exact. I don't want to square my rounded number, you know. And this comes out to 266.67 repeating. So remember, it was in hundreds of shirts, the demand in hundreds. So it's not really 266 shirts, it's 26,666.67 shirts. So the revenue is going to be $11.55 per shirt times the 26,666.67 shirts approximately. And this is about $308,000. Okay, so that concludes the lesson. So just remember that when you're trying to figure out the optimum number of units for ordering quantity and the optimum number of units for batches, when we're doing economic lot size or economic order quantity, you use the same formula. Q equals square root of 2FM over K. You use that for both scenarios. Okay, and just check with your professor. Make sure they're okay with you just jumping to this and not going through the whole derivation on an exam or something in the future. All right, hope you enjoyed the lesson. Don't forget to give the video a thumbs up, subscribe. Follow me on Instagram and TikTok, Math with Professor V. And I'll be back sooner than later with more business calc lectures for you all. Bye.